This is the presentation for the National Science Olympiad Astronomy event for the 2015 competition at the University of Nebraska in Lincoln, Nebraska on May 15th and 16th of 2015. It is meant to be just a brief overview of the content and the resources that are the most valuable to help teams and coaches prepare for the event. And I am Donna Young. As you know, I work for the Chandra Education and Public Outreach Office at SAO in Cambridge, Massachusetts. And I am the co-event supervisor for this event, have been since 1999 when it became an event. Some of you are familiar already with my co-event supervisor, Tad Kamasic, who is a doctoral student at the University of Arizona in planetary science is his area of expertise. And he is at the Planetary and Lunar Institute there. And obviously he had some input as to the topic of focus for this year, for the 2015 competition, because as you can see, it is stellar evolution and star and planet formation. So yes, the topic is exoplanets. So the Chandra X-ray Observatory has supported this event since it became an event in 1999. And the webinars will be posted on the Chandra website. Some of the deep sky objects are also in the Chandra photo album. And there is an entire section on stellar evolution that you can use to learn about any particular content that you need to look up. Another organization that has supported this, the astronomy events for several years is the American Association of Variable Star Observers in Cambridge, Massachusetts also. And on this website, if you go to the variable star menu at the top of the page and go down to educational materials and then down to Science Olympiad, you will see posted there the past events for both astronomy that are useful to download and use as study guides for the next competition. This PowerPoint will also be posted there. The link to the webinar will be posted there. Sometimes there are flashcard sets available to study. There is not one for this year's astronomy competition, but usually there are. And also, if you look at the variable star astronomy section, that is a complete manual on variable star astronomy, and there are several sections on there that talk about light curves, orbital mechanics. There is a lot of valuable information in there, not only for this year's topic, for every year's topic. So that is a good place to go and a great resource for variable stars and stellar evolution material. The parameters for the event have not changed this year, up to a team of 1 or 2 students, 2 participants, and the teams can bring either 2 laptops or 2 3-ring binders, or 1 laptop and 1 3-ring binder at your discretion. The internet access is not allowed. That is a National Science Olympiad stipulation. It would not matter in this event whether you use the internet or not, because it would not help you. The only difference this year is the topic, which is the emphasis is on the formation of stars and planets, exoplanets. The words highlighted in red are the terminology that are different this year, mostly having to do, of course, with exoplanets. There is one difference in the magnetic spectrum range. We're adding in sub-millimeter because that wavelength is good for detecting planets, exoplanets, and debris fields and disks. The orbital mechanics equations are about the same, very similar to the ones that we've had in the past, only this time they are referring to the orbital mechanics of an exoplanet and their parent star, rather than multiple stars, but the idea is the same and the relationships are the same. The new terminology here, some of the new terminology we've actually had in the past, because it still deals with stellar evolution. The only different ones are the ones that are exactly specific to exoplanets. And there are 16 deep sky objects this year that all represent various and sundry stages of planet formation. And they have been divided into 5 categories. Now, we have 2 objects that are related to star formation regions. There are 2 pre-main sequence stars. There are 4 brown dwarfs, which are also pre-main sequence stars. I'll get into that in a little bit. And the exoplanets themselves have divided into 2 categories depending upon the method of detection. So we have transiting planets, 5 objects there, and 3 objects that were directly imaged. So, the star formation, the basic star formation, starts with huge clouds of molecular hydrogen, H2. Very cold, very opaque, very dense regions of gas and dust that are distributed within the interstellar medium. The interstellar medium itself is just the gas and dust, which is a near vacuum that exists between stars. The cold molecular clouds are just much huge dense clumps of gas and dust, hundreds of thousands of light years across. They are immense, very cold. And this is where star formation has to begin, because a clump of gas and dust has to hold itself together to accrete enough material to have it become hot enough inside for fusion processes to start. And for that to happen, that little cloud of gas and dust has to be held together. That can only happen in a very cold environment. So cold molecular clouds are associated with star formation. As stars start to form and start to radiate energy, then they change the region of space around them, and then you have the development of regions of atomic hydrogen and ionized hydrogen. So this graphic is a close-up, this is a Hubble image of a region in space that started out as a cold molecular cloud, and then some clumps got large enough for the protostars inside these clumps to start emitting radiation, and that started eroding away the gas and the dust in the local region, which sculpts these really beautiful areas of pillars of gas and dust. And you can see where the light is here, that those are the regions where the stars are forming and carving this region in space-time. And you can also see in these regions the clouds of the dark clouds, the opaque clouds, where they're also called dark clouds or absorption nebulae sometimes, regions where the light cannot get through because it's still very dense and opaque. And then, and here, this one's the cold sack, actually, cold cloud, an H1 region, atomic hydrogen. And as star formation begins to form and lots of radiation is emitted by the more massive stars, then you start to see areas that are red and blue. And then they become, if the radiation emitted from these protostars heats the gas and dust in a nearby region, and it starts emitting in the red part of the spectrum, that's called an emission nebula. And then in the parts of the spectrum, parts of the region where the radiation from the star is being reflected, then it's called a reflection nebula. So there's a close association between clouds, cold molecular clouds, clouds of atomic and molecular hydrogen, and then as stars start to form, it's now called a star formation region, a stellar nursery, and you develop those H1 atomic regions and the H2 emission regions because of the reflection of the radiation coming from those stars.